In this video, we'll be investigating the effects and differences of a common compound, carbon dioxide, in its two forms, both a solid and a gas, at conditions close to standard temperature and pressure. Standard temperature and pressure is defined as 1 atmosphere and 25 degrees Celsius. Here in Colorado, at an elevation of about 5,000 feet, the current conditions are about 1 atmosphere and about 10 degrees Celsius outside. However, for purposes of this video and the behavior of our compounds, this difference will be negligible. The substance we'll be using today is called dry ice. Many of you have probably seen it used before as Halloween decorations or even as so-called dry ice bombs right here on YouTube. Why is this stuff called dry ice, and what causes this behavior that seems to be so fascinating? Dry ice gets its name from the fact that under standard conditions, the carbon dioxide cannot exist in its liquid form, as we can see here on this phase diagram. We can see here that carbon dioxide cannot exist in its liquid form below its triple point at about 5 atmospheres. Therefore, even when I leave this block of dry ice out in the midday sun, rather than melting and transforming its physical state from a solid to a liquid, as we would expect common wet ice or water ice to do, carbon dioxide undergoes a different phase change. In this case, we call the change from a solid to a gas sublimation. You may be asking yourself, if we breathe out carbon dioxide and therefore know it to be a clear, colorless gas, what's the white vapor coming off my chunk of frozen carbon dioxide that I'm holding? Or this cloud of vapor that's coming off of this over here? Actually, what's happening is that this negative 78 degree dry ice is being converted into still very cold gaseous carbon dioxide. It's much colder than the condensation point of water in the atmospheric air, so the humidity in our air is turned into effectively a cloud. Another interesting aspect that we can investigate with dry ice is the difference in molar volumes between different phases. At its sublimation point of negative 78.5 degrees Celsius, literature values for the density of solid carbon dioxide are approximately 1.562 grams per milliliter, corresponding to a molar volume of approximately 0.0282 liters per mole. However, when transformed into its gaseous state at 0 degrees Celsius, the density changes to 1.977 grams per liter, or a molar volume of approximately 22.3 liters per mole. Thus, as we can see on this scale drawing, 1 mole of solid carbon dioxide will take a space of about 28.2 milliliters, whereas the same mole of gaseous carbon dioxide will occupy a space of 22,300 milliliters. Therefore, there's approximately a 1,000-fold increase in the space occupied by the same amount of the compound when it transforms from a solid into a gas. To demonstrate this, let's place about 10 grams of dry ice into a balloon, which contains, for our purposes, no other gases. Let's tie off this balloon and see what happens. So we can see that as we let this balloon sit with the solid carbon dioxide dry ice inside of it, it's already blowing up our balloon due to the solid dry ice subliming into a gaseous state and occupying about 1,000 times more volume than the solid by itself. So let's let this sit for a moment and let this go ahead and completely sublime. Yet another interesting aspect to note about dry ice is the effect of temperature on its rate of sublimation. You can clearly see this effect by the difference here in this glass container with warm water and a chunk of dry ice in the bottom versus this piece of dry ice that I'm holding in my hand. The warm dry ice is rapidly subliming and releasing large amounts of cold carbon dioxide gas, which, as we said before, is condensing the water vapor in the air. However, it's clear that the ambient temperature around the carbon dioxide has a large effect on the rate of sublimation. This is due to the fact that the sublimation of dry ice is an endothermic process with an enthalpy of sublimation of approximately 393.5 kilojoules per mole. Therefore, as we increase the temperature around the dry ice, the rate of the forward equilibrium towards the gaseous state is increased by Le Chatelier's principle. So let's now place about the same size chunk of carbon dioxide that we placed into this balloon into another balloon here and submerge it into this warm water bath that we have prepared. So keep in mind that this green balloon up front has been sitting here for for a couple of minutes at this point and still hasn't sublimed very much. There's still a considerable amount of dry ice in there in its solid form. So let's now take this balloon, again with the same amount, same balloon, and submerge it into this warm water bath that we have prepared. We can now see that in just those few short seconds, this dry ice that's inside this balloon was warmed using this warm water bath to increase the ambient temperature, and therefore increase the rate just as we see in this demonstration here. And now the same amount of dry ice has already sublimed to the same volume as this one, except in a much shorter period of time.